is by Rajan Walia, who is going to tell us how to compile high-level descriptions of probabilistic inference code into efficient low-level implementations, and hopefully it will work. Okay. Yes, so high-level inference to efficient code.
Thank you. So in 2010, Bob Carpenter published this tech report detailing how to integrate out latent variables for LDA and naive Bayes. Now, if you don't know any of these words, don't worry about it. We'll get to that in a minute. What you need to know is that in this tech report, he performed a 25-step integral, which he says that's child's play for theoretical physicists or statisticians, but for us programmers, it's not. Maybe for some people here, but for me, it's definitely not a child's play. Even Bob says, it's amazingly difficult to get this much algebra written out. If only I had a compiler so that I could check some of these errors. Well, Bob wanted a compiler, so we built the compiler. Our compiler does what Bob would do. It takes high-level algorithms and produces efficient machine code for inferencing problems. And our compiler takes care of all the problems that Bob mentions in our tech report, but for the purpose of this talk, I'm going to start with a simpler example, which is similar. In this example, let's say there are some balls on a real line, and they have some labels attached to them. And there's a new ball which we don't know the label of, and we want to guess the label of this unknown ball. To solve this problem, let's say there are some sources up above which are dropping these balls with these labels. And if we can somehow find the location of these sources, we can use that location to guess the label of the ball by using the proximity of which source is close. But this is a talk about probabilistic programming. We don't just want to guess the label. We want to get the distribution of labels for this known ball. To do that, we have these cause, which is the sources, and the effect is balls on the number line. But what we are trying to do is opposite. We are trying to infer the location of the sources from the location of balls. Let's even complicate this problem even more. Let's say we have n balls and m labels. Now, how would you solve this problem? Well, if you're thinking of using averaging, you're on the right track. We average the location of balls with a given label to get the source location. And once we have that, we can use something like argmin to guess the label of our new ball. But again, we don't just want to guess it. We want to get the distribution of labels out. To do that, we use our programming language to build a probability model. So let's see how we'll build a probability model for this problem. We have these sources. We say these sources are lying somewhere around origin with a standard deviation of 17. And we say that the label of balls come from a distribution with equal probability for 0 and 1. And once we have both source location and a label, we can guess the location of our ball by saying if its label is 0, then it's somewhere around source 0. If its label is 1, then it's somewhere around source 1. And we do the same thing for our new ball. And once we have this probability model, we can use it to infer the source location or the label of the unknown ball by using the location and labels of the known balls. Now let's see how we'll write this problem with n balls and m labels. Now, we added arrays to represent n balls and m labels, so we add arrays to our programming language. We add this notion of plate to define a probability distribution over arrays given a distribution over a single index. So here, each index in the array has a probability distribution of normal 0, 17, but sources is an array of locations. And we do the same thing for our ball labels. We use plate, again, with categorical to get the labels of our balls. And once we have labels and sources, we can, again, use both these arrays to directly figure out what position our ball will be according to its label and source. And something similar with our new ball. And then once we have this, we use our probability distribution to get to infer our new label. So we have this probability distribution, and we use our language to generate efficient code out of it. But what Bob did is these source locations, these are redundant. They are not in the input, they're not in the output, but they come in our model. So we want to optimize those out. And we want to directly go from the label of known balls to the unknown label. And that's the problem we solved, and that's the problem that Bob solved in his paper, and that's called eliminating latent variables. And so we call this problem as simplification, and that's the first step that I'm going to show, and that's what we did in our compiler. So simplifying array probabilistic programs need two things. We need to perform high and arbitrary dimension integrals, which is completely opposite from previous talks. We are going to do integrations in this one. And we need to perform recognize high and arbitrary dimension densities. We do both of these things using computer algebra systems, but we came up with a semantic operation called unproduct to do some of these things, which computer algebra systems don't do. So in this talk, let's just look at the first one, which is integrating out latent variables in high dimension integrals. So this is an expression that comes up when we are simplifying the problem that we just solved. And we want to integrate this expression. This is a high dimension integral where 0, 1 to m there are like m integrals with each limit 0 to 1. So how would you integrate this out? Well, let's look at a simple instantiation of this problem. Let's say y is 0, 1, 2 to 1, and m is just 3. Now, this is a simple problem where we are just trying to integrate over 3 dimensions. And to do that, we just look at the body of the integral, and we factor out each variable separately. We say we separate each variable out, and once we do that, that's the unproduct operation. And once we do that, we can distribute the integral inside, and then we can use our computer algebra systems to calculate this integral. So we want to do something similar for our complicated example. And what we do is we again rewrite this expression in such a way that we are using each index of an array separately. So if we look at this expression, we are using x0, and we calculate how many times x0 occurs in that product, how many times x1 occurs in that product, and so on. But what does this give us? What does this rewriting give us? Well, once we have this, what we can do is we can take the outermost product out of the integral. And when we do that, we go from a higher dimension integral of dimension m to a single dimension one. And once that happens, we can again use our computer algebra systems to calculate this integral out. And this is a simple integral of just power to the x, and which is 1 over 1 plus the power of the x. So that's the unproduct operation, how we use unproduct along with computer algebra system to solve this problem of integrating high and arbitrary dimension integrals. So let's look at how we do this. What we want to do is we want to rewrite this expression into something which looks like the right-hand side. So we write this as a function which takes the expression and the array variable which we are integrating over, and it returns a residual expression, which is just 1 in this case, and a function that looks at each index of the array separately. So here, this function will not contain xi as a free variable. It will only depend on the xi, which is the input of this function. And the way, in practice, we implement unproduct using an accumulator, where accumulator is an expression with a context. And we look at the expression. We have a pi in our expression. We just move that pi to context. And if we see an indexing operation with the same array variable, we convert it into a conditional, and we get the expression that we want. And we use this, again, to rewrite our expression into something that computer algebra systems can handle. So that's the unproduct operation. Now, once we have done the unproduct, we get these expression out. We get this expression. We want to compile this expression into efficient code. If somebody like our programmers or humans can look at it, and we'll compile it into efficient code with using an array. We'll calculate the summation for all of the i's in single go once, and then we'll use that array inside the pi loop. So we go from a quadratic time algorithm to a linear one. But we are going from pure language to impure. If we directly go from pure to impure, it's really hard to perform this optimization. So what we want is, we want to do something, we want to have a pure language which can represent both sigma and the array loop optimization that we have. To do that, we came up with this pure reducer language which can express this. So here, the hist expresses the loop and the sigma. The IDX expresses what the condition we have in our sigma loop, and the one expresses the increment that we are doing in our arrays. Once we do this, our hist expression is pure, and we can perform loop invariant code motion on pure expressions, and we can get the expression that we want by then expanding it to pure code, impure code. So again, this is the histogram optimization, and let's look at how we do this. Again, we have this expression on left-hand side, and we want to rewrite it into something that looks like on right-hand side. And we use this function, which takes the body of the loop and the variable that we are looping over, and returns a reducer and a function that tells us how to use that reducer. So here, we take this body and j, and when we see a condition, we directly convert it into an IDX, where the second part is the result of the recursive call to 1, where histogram of 1 is just add 1, so we just use add 1 in there, and then we get what we want. So once we have done this, we want to do code generation, efficient code generation for these kind of things. And we use our domain-specific properties to perform many compiler optimizations aggressively, which are again, not that easy to perform in general-purpose programming languages. Like loop invariant code motion is really easy to perform in pure code the way we do it. And most of the Haku programs are used inside a loop, outer loop, by repeatedly invocation on same arrays. So we know that our array sizes are going to be same, and we use that to specialize our compilation on the size of arrays. And when we know the size of input arrays, we also know the size of intermediate arrays, and we can pre-compile those arrays before even compilation. So let's look at how we perform with other languages. Because there are no other probabilistic programming languages that do what we are trying to do, we only try to see that we are in the ballpark of other programming languages. So what I want you to get out of this is, even though we are doing a lot of things automatically where other people have done by hand, we are still in the ballpark of the performance. And this is the problem. This is one of the problems that Bob solved. And here also we can see we are in ballpark of other probabilistic programming language. And let's also look at how these optimizations help us. These optimizations like histogram and LICM, they work together to give us performance benefits. Each of them by themselves don't give us enough performance that we need, but when they work together, they really outperform all the other optimizations. And that's how we implemented the compiler that Bob wants by having these 3 steps. The simplification, where we perform high and arbitrary dimension integrals. Histogram optimization, where we convert quadratic loops into linear loops. And then we came up with a pure reducer language for that. And then we used domain-specific optimizations to perform generate highly efficient code for our language. Thank you.
Okay, so we have plenty of time for questions. Okay, let's just try one from online. Can you comment on why lifting multiplications outside the integer is allowed? Do you use an SMT solver to prove it's valid, or anything like that?
No, we don't use an SMT solver. We use a computer algebra system to perform the integrals, but other than that, the unproduct and those things, we do them by ourselves.
Okay. Are there any questions from the floor? First one, yeah.
What was your experience working with the computer algebra systems on this project? I
didn't do that. I I did the compiler parts of this. Maybe people who did that, maybe they can answer.
So another one from Slido. Previous versions of Hackaroo could fail to produce an executable. Does this version have any points of failure? And if so, why? Or what are they?
Well, all the research software have some points of failure.
Any other questions from the floor? That's one.
Why are you targeting x86 machine code? I would expect some higher level backend.
So we use LLVM to generate x86 machine code, which can generate other machine code as well.
Have you integrated with this with your previous work on disintegration?
Yes.
Yes. So I have a question. So I didn't quite understand the performance graphs. Could you, what does the accuracy thing mean?
Accuracy?
Yeah. So are you?
So this is a Gaussian mixture. This is a more complicated problem than the ball problem that we saw.
Mm-hmm.
In this problem, we don't know any of the labels. We just have balls of real line. So the accuracy is once we calculate the labels, how well that the labels that we got compares to the actual labels that we have.
Right. Okay. So this is saying that you're slightly slower to get good accuracy, but you get better accuracy in the end.
Yeah.
So you've applied this to probabilistic inference algorithms. Does it apply to any other kind of numerical computing?
We haven't tried it. It might, I think the histogram and simplification problems are very general problems that can be used in other areas as well.
Questions from the floor? Okay. Thank you. Let's move on. Thank you.